All right, let's do question 7. I don't like green, so let's go with black. Sure. Okay. So question 7. At a certain temperature, the equilibrium constant for the following reaction is 75. I believe that's ozone. Don't quote me on that, but let's just call it ozone. 2 ozone molecules form 3 oxygen gas molecules. And the reaction goes back and forth. 0.3 moles of ozone and 1.5 moles of oxygen were introduced to a 5-liter reaction vessel. Which row of the table correctly identifies the direction of the equilibrium shift and the reason for the shift? Alright. This question, I think it's useful for understanding the difference between the reaction quotient and the equilibrium constant, because these two are not the same thing. And we're going to see what the difference is. We're going to try and understand what the difference is. First of all, I just want to label this so that to bring it to attention, so that we don't make this mistake. We know that concentration equals moles divided by volume. So we have to be careful in this question because the volume is not 1 liter, it's 5 liters. So when we're calculating the concentrations of oxygen and ozone, we have to divide it by 5. We have to remember to divide it by 5. We can't just use moles because these are just the moles. These are not moles per liter. We have to divide by 5. So let's write the equilibrium. So this dot point is relevant here. Perform calculations to find the value of K of the equilibrium constant and concentrations of substances within an equilibrium system, and use these values to make predictions on the direction in which a reaction may proceed. So this question is actually a direct translation of how they might test you on that dot point, and it's also deducing the equilibrium expression. So let's write the equilibrium expression. Now we're going to write Q equals products over reactants. And I'll explain to you why we use Q. I'll try and explain the difference between Q and KEQ. So KEQ is, think of it as the ideal, or the both K and Q, we define as the ratio of products to reactants. Yeah. The only difference is that K is the equilibrium ratio. So what will the ratio of products to reactants be when equilibrium is reached? A system doesn't need to be at equilibrium at all times. Over time, the system will go towards equilibrium. It will try and reach equilibrium. But for example, if you just introduced some of the reactants and some of the products to a reaction vessel at time equals 0, the system is not necessarily at equilibrium. So the ratio of products to reactants at time equals 0, when the system is not at equilibrium, that is defined by the reaction quotient. Okay, so again, K, the equilibrium constant, represents the ratio of products to reactants at equilibrium, at any other point in time when the, for example, before the system has reached equilibrium, the ratio of products to reactants is labeled Q, the reaction quotient. Once equilibrium has been reached and the ratio of products to reactants is not changing because the forward and reverse reaction are happening at the same rate, then we label it as K. Right, so let's calculate Q. So Q equals the ratio of products to reactants. The equation is exactly the same. How you form the expression for Q is exactly the same as how you form the expression for K. So it will be O2, it will be the products raised to their coefficients divided by the reactants raised to their coefficients. O2, oxygen cubed divided by, so the concentration of oxygen cubed divided by the concentration of ozone squared. The concentrations being, so remember, concentration equals moles divided by volume. So the concentration of oxygen is 1.5 divided by 5, the whole thing cubed. And the concentration of ozone is 0.3 divided by 5, the whole thing cubed. The whole thing squared. Alright, so let's open up the calculator and see what this will evaluate to. 1.5 divided by 5 to the power of 3 divided by 0.3 divided by 5 to the power of 2. This evaluates to 7.5. So Q equals 7.5. So we know that KEQ is 75. K, the equilibrium ratio of products to reactants is 75. Q, the current right now, the ratio of products to reactants is 7.5. So Q is less than KEQ, right? Q is less than KEQ. 7.5 is less than 75, which means that the reaction is not at equilibrium. The ratio of products to reactants is not the equilibrium ratio. It's not 75. So the direction the reaction will move in is towards the right. So Q is less than KEQ, and the direction favored is to the right. So we already know C and A would be wrong because we just calculated Q. We know that Q is less than KEQ, and B would be wrong because if the reaction went in the reverse direction, let's see what would happen if the reaction went in the reverse direction. If it went to the left, more ozone would be formed. The concentration of ozone would increase, right? So in this equilibrium, in this expression, the concentration of ozone goes up, so the denominator gets larger. So what you're dividing by gets larger as well, which means that the value of this expression will actually go down because you're dividing it by something larger. So right now it's 7.5. As you increase the denominator and shift to the left, it will actually go down to 6, down to 5, 4, and further and further down if the reaction went to the left. But if the reaction went to the right and more oxygen was formed, then the numerator gets larger and larger until it eventually reaches 75. So it'll go from 7.5, we'll go to 10, 20, 30. The numerator keeps getting larger until it reaches 75, and then it stops at 75 because that is the equilibrium ratio of products to reactants. That is the ideal, you can call it the ideal ratio. It is the ratio that the system is trying to reach. Yep, so when Q equals KEQ, the equilibrium has been reached. So when Q being what is the current ratio of products to reactants, when Q is equal to KEQ, K being what is the equilibrium ratio of products to reactants. So when the current ratio of products to reactants is equal to the equilibrium ratio of products to reactants, then we say that equilibrium has been reached, and the reaction doesn't proceed in either direction. The rate of forward and reverse reaction is equal. But for now, since Q is less than KEQ, the reaction goes to the right. And let's just check the answer. Yep, so the answer is D, which is what we selected. So we selected D, and the answer is D. Cool.